Okay. So if I draw all the currents here, I label them as I1, I2, I3, I4. So I think you know that the formula for the current is I1 plus I2 equal to I3 plus I4. Okay, it's total current into the junction equal to total current out of the junction. So how we derive this law? So why it is derived from the conservation of charge? So we consider the charge at the junction. We consider the charge at the junction. So these two currents will there will be some charge coming in the junction, and then there will be some charge falling out of the junction in I3 and I4. So if the charge at this junction is conserved, so what does it mean by conserved? That means the increase, the amount increase equal to the amount decrease, then the charge is conserved at the junction. So that's why we say that, and then you divide the charge by time, you get the current, is it? So the charge going into the junction equal to the charge going out of the junction. And then you divide by the time, you get the current in the junction and current out of the junction. So that's how we derive from the concept of charge. Even you don't know how to derive it, it doesn't matter. Okay? You just need to remember that it is derived from the concept of charge. So the first law is quite simple. The second law is much more difficult. So we need to spend at least one lesson to talk about the second law. So it is derived from the concept of charge. So conservation of energy. And then the statement, you need to memorize the statement because you may be asked in a long question. So the statement is like this. Around a loop, I'll talk about what does it mean by loop. So around a loop, the sum of the EMF is equal to the sum of the potential difference. So can someone tell me what is the difference between the EMF and the potential difference? Hello, hello. No one? Peter, leh?
Yeah.
So what does it mean by EMF? I'm not just asking your name. I asked you to answer the question.
Oh, EMF is electromagnetic force. I don't know.
I'm asking you the difference between the EMF and potential difference. Samuel, Samuel, you look very smart.
EMF is electromotive force, and it is the energy gained per charge
So
from a power source.
How about potential difference?
It is the energy lost per charge when passing through a component.
Yeah. So let me write down the definition here again. So EMF so it is, you say that is an electrical energy gained per charge. And for the potential difference, so you say the electrical energy dissipated or lost. I will say dissipated. Let me see. So there's electrical energy dissipated per charge. So what does mean by loop? So let me ask you a kindergarten mathematics questions. Yeah, I'm so happy. So let's say let's say there's a Chinese character. That means day. So how many rectangles are there in this character? So you can show me your fingers, okay? Is it all of you get the same answer? Okay, so all of you say 3, is it? So let me draw them out, okay? So 1, 2, and 3, is it? 1, 2, and 3. So all the circuit look like this form. So all the circuit look like this form, and then you can always find the rectangles of these or in the circuit. So let me show you some circuit. Okay, like this. Okay. So we can form a rectangle here. Is it? So for this circle, okay, you can form a rectangle here. You can also form a rectangle here. But it doesn't look like a rectangle. So a loop doesn't mean it's not always a rectangle. Okay, it can any closed path. So in this case, for the circuit here, okay, you can actually form 3 different paths. 1, 2, and 3. Can you see it? 1, 2, and 3. There are 3 different paths. Okay, so you say 3 different loops, 3 different loops, and you are using these loops to and then for each loop, around each loop, the sum of the EMF is still equal to the sum of the potential difference. So we are going to talk about these examples one by one. You're so happy that unlike the Form 6 students, they need to wake up so early and go back to school. And then you can still stay at home, enjoy the lesson. Okay, so let's have a look at this question, okay? If you get it wrong, you copy the first page 100 times. So I'll let you to answer the question. Okay, one of you is fired. And then I don't know what to say, okay? Right, this is just a reading comprehension. Do you see from the question? So first law, derived from the concept of charge. So the answer should be A. Like who answered B? Okay, you should. So hand in the copy tomorrow. 100 times. Okay, so there are many questions look like this format. Okay, so these are already the simplest question. You just need to notice what law or what constitutional law is derived the first law and the second law. So then let's go into the details of the Kirchhoff second law. So I divide into battery and resistor because most of the circuit you encounter is just consists of the battery and the resistors or the light bulb. So first of all, let's have a look at the battery. So around the loop, let's have the pictorial explanation first. This one. So you know, this is the water pump, and then we consider the current as the water flow. So the charge is the water. So if you look at this picture, what you can see is, what you can interpret is, let's say around a loop. So let me draw the loop first, okay? This loop, this one, okay, this is the loop. Okay. And also you should indicate the direction of the loop. So let's say I say the direction of the loop follows the direction of current, okay? You can also choose the loop not following the direction of current. It doesn't matter. It's still fine. So if you follow the direction of current, okay? So let's say initially, so let's say initially, okay, let's say who is very sleepy. Okay, Marcus, hello. Okay, initial Marcus is here, okay? And after going to a pump, he gains the potential energy. Okay, he gains the potential energy. And then going down the slopes, and then he loses the potential energy and go back to the bottom of the pump. So what does it mean here? So that means overall around a loop, the overall energy change of him is 0. So it goes from point A, so there's some point labeled, okay? So it goes from the point C to point A to point B, and then go back to point C, okay? So let me write it down first. So it goes from the point C to B, so to A to B, and then go back to C. So the overall change in energy is 0. There's no overall, when you go back to C, the P is still the same. He loses all of the energy. So in around this loop, he gained energy from the water pump. So energy gained from the water pump. And he loses all the energy through the resistors. That means the slopes. So that is equal to energy lost by the slopes. That means the resistors, okay? So that means you can see the energy gain equal to total energy lost by the slopes. And then if you divide by the charge, so on the left-hand side is energy gain per charge. And then on the right-hand side is energy lost by the charge. Okay. So they will be equivalent. And then, okay. And then if you still remember the definition of EMF and also the PD, so that means the EMF equal to a PD. Okay. So this is how we can interpret the second law from this diagram. And so the most trickiest part comes. So you know, I told you that you can choose the direction of the loop. And then if you choose the direction of the loop in different direction, and then sometimes the EMF will be taken positive and sometimes the EMF will be taken negative. So let me tell you this rule first, okay? So for the battery, that means the EMF. So EMF is taken positive, 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 positive. If it's going from low potential to high potential. So I give you the full picture here is much more clear, I think. So that means if you are going from the negative terminal to positive terminal, and then your EMF is taken to be positive. So the orange arrows means the direction of the loop. The orange arrow means the direction of the loop. So if you're going from, this is the positive negative terminal to positive terminal. Negative terminal means low potential, and the positive terminal means high potential. And then in this case, the EMF is taken to be positive. So that means, let's say if this battery is 1.5 volts, and then you take it to be positive 1.5 volts. Okay, positive 1.5 volt. But if your direction of the loop is opposite, so let's say this case, okay, and then you take the EMF to be negative 1.5 volt. You take it to be negative 1.5 volt. So we will do a lot of practice today, so no worry about it. Okay, is it clear? So then let's have a look at the resistor. Resistor is not that difficult, okay? So you can see the PD is taken to be positive if going from the high potential to low potential. So if difficult to memorize, maybe. So what you can memorize is if the direction if the direction of the current follows the direction of the loop, and then you take it to be positive. Okay, it's easy. If the direction of loop is opposite to the direction of current, and then you take it to be negative. Okay. So let's do some practice, okay? I understand this will be quite confusing and it's maybe quite difficult. So let's have a look at this example first, okay? Let's have a look at this example first. Let's say this one. No, this example first. I have given you the direction of the current already. And let's say I make the loop like this, okay? I make the loop like this. So this is a closed path, okay? Closed path. So the current, okay, the direction of current follow this direction. That means it's I and this I downwards. So if you write down the new Kirchhoff second law, so the format of the Kirchhoff second law is sum of EMF equal to the sum of the PD, potential difference. Okay. Then for the EMF, so which one will give you the EMF? This tube battery will give you the EMF. This one and this one, okay? So let's have a look at how we take the value of the EMF. So let's go back, have a look. So if it's going from negative terminal to positive terminal, and then you take it to be positive, okay? From negative to positive, you take it to positive. You take it to be positive. So if you look at the battery 1, E1, so you see the direction of the loop. So and then the EMF is going from negative to positive. Can you see it? So going from negative to positive. So you take it to be positive. The EMF, you take it to be positive. So that means it should be the positive E1. Okay, positive E1. Okay, if you look at the battery E2, okay, and then you see the direction of the loop goes from the positive terminal to the negative terminal. And then if go from positive terminal to negative terminal, you take it to be negative. So that means here it is negative E2. Okay, so this is a sum of the EMF. You should follow the format like what I did. And some of the PD is much more easier because you just need to identify whether the direction of the loop follows the direction of current. If yes, take it to be positive. So for the PD, we are talking about the resistors. So there are two resistors here, R1 and R2. So if you look at the resistor R1, okay, the direction of the loop follows the direction of the current, okay? Can you see? So you take it to be positive. Same as the resistor R2, the direction of current follows the direction of the loop. So you take it to be positive also. So that means the PD of R1 resistor. Okay, let me ask. So Anna, how can we express the PD of the resistor R1? Because the EMF is labeled as E1 and E2. How about the PD of the resistor R1 and R2? Anna is lost. Hello, Anna.
Hello.
Hello.
I'm not sure.
We are using the law, the only law you used previously. That's the Ohm's law. To still remember V equal IR. So the PD of the resistor R1 is the current I times R1, okay? And you take it to be positive, I times R1. And then similarly for the resistor R2, you take the PD to be positive. So it should be positive I times R2. So make sure you understand this simple example. Okay.
Sir, how do you determine the direction of the loop?
You take it by yourself. You can take it to be clockwise or anti-clockwise. But I rather you follow the direction of current if you can. So you take the loop which follows the direction of current. Then it's easier for you to write down the sum of PD. So this is a good question because in some of the case, actually in the question below, you need to determine how you write, how you should decide the direction of loop by yourself. Okay, so following the example 1, let's have a look at the example 2. So I rather you're not looking at the choices, okay? I rather you're not looking at the choices. And I rather you can write down the equation by yourself. Yeah. Okay. So this is just, you can, for example 2, for this circuit, there's only one loop, is it? There's only one loop you can form. And then for the loop, I rather you follow the direction of the current. So it gives you the direction of current to be in this direction. So you follow the direction of current, like, so that means the loop should be taken in this direction, clockwise, anti-clockwise. So I'll give you 1 minute to write down the equation for this case. Let me wear the glasses, okay? Yeah. Okay, 1 minute passed. So can you type the answer in the Zoom chat? So Pardon and Samuel gives the same answer. Peter gives the same answer. Okay, Veronica gives the same answer. So for the sum of the PD is quite simple, is it? Because all the direction of the current follows the direction of the loop. So all the PD take to be positive. But for the EMF, it's more difficult because, okay, I think most of you get the answer. So let me, dear, you just make it opposite. I think. Oh, so the direction of current is like this. And then for V1, you take it to be positive because it's going from the negative terminal to positive terminal. Okay? So you take it to be positive. V2, you look at the direction of current. You're going from positive to negative. So you take positive terminal to negative terminal. So you take this EMF to be negative. So same as V3, you take it to be negative. So most of you get it correct. So the answer should be D for dot. Okay? D for dot. If no question, and then let's go to the example 3. So this may be a challenging question. Now, the current is not given in this question. You don't know whether the current flows from, actually, I think you should know it. Okay. So now you don't know whether, what is the direction of current. So let me take the direction of current to be like this, okay? You may see something interesting, okay? You may see something interesting. So, and then you use the Kirchhoff second law to solve it. You use the Kirchhoff second law to solve it, okay? So in this kind of question, you need to let the direction of the current by yourself. It doesn't. It's fine if your choice is wrong. It's totally fine. And then you need to decide the direction of loop by yourself. Okay. And then you use the second law to solve it. So what I mean by solve the equation is to find the current. If you can find the current in the circuit, then you can find everything in the circuit. That means you can find the PD, you can find the EMF, you can find the power, you can find energy. Okay, you can solve anything in the circuit. 0.4除So Winnie and Caspar, yeah, you get it correct. Okay, so let me ask. So you do something similar as this question, but in this question, you need to substitute the value and solve the current. So most of you get it correct. So. Oh, so George, can you write down the formula?
Write down the formula, like I equals B over R.
I mean a Kirchhoff second law. Steph, the equation like this, okay? So what is the sum of EMF? I'll not give, so 2 plus 1.6 or 2 minus 1.6 or
So it's 0.4, right?
No.
No.
So the direction of loop, what do you choose? Do you choose like this one?
I went with the current.
Yeah. So
Yeah.
if you let the current direction like what I did, and then
Negative.
so you take the EMF of cell X to negative, okay? So that's -2, is it? -2 here. Okay, this one is -2 because you go from the positive terminal to negative terminal. And then for the EMF of 1.6, you take it to be positive because you go from negative terminal to positive terminal. Okay, then that equal to, this is sum of the EMF, equal to the sum of the PD. So all the currents are the same and all the PD is positive. So I group the current I out from the circuit. Okay. This is what you find, how you solve this equation, how you write down this equation. Then I think most of you can solve it already. So what you, don't ignore the negative sign. The negative sign means something, right? So for the left-hand side, you get negative 0.4. That equal to I times 4. So that means you solve the current to be negative 1.0. Is it? So what this negative mean? It means that your choice of current is wrong. Then that means the current should be down the 0.6 X Okay, that means the actual current should be downwards like this. Okay, if you calculate the current to be net value, that means it should be in the opposite direction as what you stated. And so you may wonder, how about if we let the initial current to be downwards like this one, and we take the loop in this direction, following the direction of current. And then if you write down the equation, you get +2 plus -1.6. So then equal to I times 2 plus 0.8 plus 1.2. then the current you calculated will be 0.1 and positive 0.1. That means your choice of the current is correct. Okay. So this is the example of this one. You see, this is from your past paper, MC. Okay, I think most of you have mastered this one already. So then let's have a look at the next example is more difficult. So in this case, so this is a letter like this. So as you know, you can form 3 different loops. You can form 3 different loops. 1, 2, and 3. Is it? Because you have learned it from kindergarten. You know the kindergarten mathematics. So you can write down. Okay. Maybe let you try. So, you form 3 loops. I hope you can write down the equation of the 3 loops by yourself. And for this one, for this loop, I think that you follow the direction that is the clockwise direction, is it? Because you follow the direction of current. And then for this loop, I think you follow the direction of the I3 any clockwise direction because it follows the direction current. Okay, so that's 2 loop. What loop 1 and loop 2? So first of all, I want you to write down the equation first of loop 1 and loop 2. And then you need to solve it. And remember, the direction in each resistor are not the same. They are labeled as I1, I2, and I3. They are different. We still have just 4 minutes. So we just finish this question by today. 快啲啦， we have recess 啦。 And then I can go to sleep 啦。 Winnie asked a good question, but let me answer you later on. First of all, you write down the equation. So for the equation of loop 1, okay? So the sum of the EMF is 15. Simple, is it? Because there's only one battery there. And then it's going from the negative terminal to positive terminal. So you take the EMF to be positive. And then for the loop 1, and then the sum of the PD, both current follows the direction of the loop. So you take both PD to be positive. So you get I1 times 2, that means 2I1, okay? And then plus 2I2. That's it. Is it how you write down this equation? And then let's go to the loop 2, okay? Loop 2. For the loop 2, there's only one battery. So the EMF is 9. So the loop goes from the negative terminal to the positive terminal. So you take it to be positive 9. And then for the PD, both current follows the direction of the loop. So you take both PD to be positive. So there's 2I 2 plus 2i3. Okay. So that's how you write down these two equations. Okay. That's how you write down these two equations. But you may wonder, okay, because there are three unknowns. So I'm not giving you the choice first, okay? I'm not giving you the choice first. If you are given the choice, you can substitute in this formula to see which one is correct. I'm just teaching you how to solve it in general. So yeah, there are three unknowns, I1, I2, and I3. But you have only two equations. You know you can't solve three unknowns by just using two equations. You still need to use the third, one more equation to solve it. So what equation else you can use it? Nonica, hello. So what, any equation you can think of, any other equation you can think of to write down?
The one of the bigger loop, like the
Yes, okay. So Nonica gave a good idea. So the one with the bigger loop, Caspar. Caspar is playing the game with his iPad. Caspar, what any other equation that you can think of? Except the larger loop.
I'm not sure. I use simultaneous equation to solve the question.
But you have only two equations. You can't solve three unknowns.
Yeah, I subbed it in.
You can't. Then you just use two equations to solve three unknowns.
Oh no, I have the MC. I just put the numbers in.
Aye, so bad, so bad.
Wait, what's wrong with that? Wait, what's wrong with that, sir?
So bad. That means you are not understand how to solve it, lor. Now, you can use the equation of the bigger loop. Anyone have any other choice? No? So let me solve it faster, okay? We don't have time left. So for the bigger loop, so if you go as the direction of what I state, so for the there are two batteries in this loop. So one take positive and one take negative because of the direction. For the 9-volt battery, take it to be positive. For the 15-volt battery, take it to be negative. So it's 9 minus 15. And then for the sum of the PD, so the I3 follows the direction of loop, but I1 does not follow the direction of the loop. So I1, that means the I1 resistor should take negative, and the I3 should take positive. Okay, right now you have three equations, and then you can use your calculator. The calculator can solve the simultaneous equation up to 4 unknowns. You just substitute in your calculator, and then you can solve these 3 unknowns. But to be a smart student, actually, you can use this one or another one. Many students may always forget, if you are starting to learn a second law, you always forget that you have a simpler law, that is the first law. So you can use the first law to relate I1, I2, and I3 also. If you look at this junction, this one, okay? So I1 and I3 are the current into the junction. I2 is a current out of the junction. So by using the first law, you can write down I1 plus I3 equal to I2. Okay. So right now, we're so complicated. There are 4 laws here, okay? 4 equations here. You can choose either 3 of them to solve the equation. Okay. So for me, I will not write down the equation 3 because it's always very complicated to use the second law. It's always very simple and simplest to use the first law. Okay. And also, you know this question is MC, it's not long questions. So after you write down the first two equations, actually you can substitute in the value to see which one is correct. It's fine, it's totally fine. So is it okay? So we just have 2 more minutes, okay? Then see you all tomorrow at school. I've prepared the experiment of the circuit for you tomorrow.
In school?
Isn't that you go back to school tomorrow? Huh?
Wait, so are we supposed to go to school since morning? Like, or are we supposed to?
No, you just go back from just after the 4th lesson. You don't need to go back to school in the morning.
Is it for just tomorrow, right?
You for other weekend by you have different timetable. For physics, I think for physics it should be. Let me see. And also I will confirm you, and then tell you from the in the morning in the WhatsApp. So我想講咩啱啱？What you want to ask? I'll confirm you in the WhatsApp, okay? But I think after your 4th lesson, okay, you need to go back. You need to arrive at maybe 2:50, okay, and then go to the physics lab for the practical lesson. But so do you all know that you need to go back to school on Wednesday? You are not having the 5th lesson, yeah. You are not having the 5th lesson because the 5th lesson is for your travel time. Okay. Is it okay? So for physics, it is always at on week A Wednesday. I'm not sure your other subjects. Let's say the chemistry and biology, they also have the practical. Casper, can you share the email, the timetable in the WhatsApp? Casper,
Huh? Yeah.
can you find out the email and then send in the WhatsApp?
Isn't it a direct message on sector?
Is it?
Yeah.
Or can you share the message to?
Yeah, okay.
Okay, so then. Okay, then see you all tomorrow, okay? Bye-bye.
Bye, sir. Thank you.
Bye. Bye-bye.